Hello everybody. So I want to prepare you for a quiz that this will be on Euler circuits. I'm not going to do Hamilton circuits yet, but Euler circuits, because we have a good algorithm for that. And so the first question here is, you see a drawing, and the question is, can you draw this without lifting your pencil and without retracing? I hope that is clear, that that's part of the game, if you want. So what we need to do is, well, first of all, this is not a graph per se, but we can make it into a graph by using all the intersection points as the vertices. So let's do that first. So that's we would have a vertex here, one there, one there, one there, one there, one there, here, 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 and here. These are all the places where these lines intersect or connect, okay? And then these are the vertices. Now we have a graph. And does this graph have an Euler circuit or does it have an Euler path? So, okay, I said Euler circuits, but perhaps I should also add here Euler circuits or paths, right? It's either or other. Because when it comes to drawing, it doesn't matter that you start and end at the same point. In fact, that's kind of a bit, well, it's not, if you draw a circle, that's what you do. But if you draw a picture like that, there's no stipulation that it has to be a circuit. It can be a path. So what we need to know is the degrees. That will tell us everything. So let's mark on all the degrees. That's 3, that's 2, that's 1, 2, 3, 1, 2, 3, 1, 2, 3. I hope by now you see that something is awfully wrong. Because as if for an Euler circuit there should be no odd degree, for an Euler path there should be 2 odd degrees, and everything else doesn't work. So too many odd degrees means no Euler path or circuit. And so no, you cannot never draw this thing just once. Okay? So that was an easy example. Now I want to do a slightly different problem using the same picture, but so I'm gonna have to I probably have to redraw it because you'll see. So I'm going to redraw the same picture. And now let's think of this as rooms. This is a house. So let me pose the question. Is it possible to draw a line, without lifting again the point, that goes through every edge exactly once? Okay, so what I mean is I can start wherever I want. I can start from the outside, I can start somewhere inside, but for instance, so there, and then there, and then there, something like that, and I don't know, did I cover everything or not? That's the question. Can I do this? Can I not do this? Okay, so perhaps a better formulation would be, think of this as a house, and every wall has exactly one door. Yeah, so perhaps I should have mentioned that when I say draw a line through each of the edges to each of these line segments, I mean you can of course not go to a corner, right? You have to go somewhere in the middle. Okay, so perhaps better to say, is it possible to draw a curved line such that it passes through the middle of each of these line segments exactly once? Okay. So it's a bit similar here as the Euler problem. And so let's therefore formulate it in that sense. So what when we think? We should think of each of these as doors. Each one has a single door, okay? And so it's a door connects these two regions. Of course, these are the 5 rooms, but there's then the outside yard. Okay? So it's very similar to the regions in Euler's Königsberg, in the city, and the bridges are here, the doors. Now remember, what that meant was that the regions become the vertices of a new graph. So we're not using this now as a graph, or it's not this, the one that I just had before. It's going to be different. So let's call these rooms, let's give them names. This is room A, this is room B. I'm using small letters because I'm going to use them as vertices. Room C, room D, room E, and F is the outside. So we have now a graph with 6 A, B, C, D, E, and F. And now we want to write down what are the possible, what are the edges in this graph. And remember, there's an edge if you can go from one room to the other via a door. Okay, if there is a door that leads from A to B, for instance. So let's start from A. From A, I can go definitely outside. Well, I can go outside in two different ways. So it's going to be a multigraph because it is one door here and there's one door there. So there are two edges from A to F. It's a multigraph. And of course, from F to A, it's the same thing. Then from A to C, there's only one way. From A to D, there's only one way to do it. From A to B, only one. And from A to E is not even possible. You understand? So I emphasize, since this room has, each wall has exactly one door, right? This is the door that leads from A to C. This is the door from A to D, the door from A to B. And these two doors, so the 1, 2, 3, 4, 5 doors, right? These two doors are going to lead to F. So 1, 2, 3, 4, 5. There are 5 doors, so 5 edges. And let's do this for B. Well, from B, I can go to A. I know that already. There are two ways to go to F. Now, remember, F is the whole outside, right? So I can go this way. Oops. I can go this way and I can go this way. There are 2 doors, so I get from B to F in a multigraph like that. Then I can go from B to D. I can go from B to C. No, but from B to E. That's possible. All right. And again, 1, 2, 3, 4, 5, because there are 5 doors in B. Now, C only has 4 doors, so let's see that that's reflected. From C, there are again 2 ways of going outside. There are 2 doors that lead me outside, so there's going to be 1 and 2. Okay? But then there's 1 from C to A, which I already have, and 1 from C to D. That's the next one. All right. D has 1, 2, 3, 4, 5 doors again, and 1 goes to A, that I have, 1 goes to B, I have, 1 goes to C, I have that, 1 goes to E, and 1 goes to F. D is kind of a little bit the central room, right? You can go anywhere from D. And from E, finally E, most of it I have, except for how can I go to F? And there are, again, 2 doors that lead outside. So that's, from E to F is 1 and 2. And that's it, right? Because from E to D, E to B, that's the only 2 possibilities. I have already those 2. So now this is a graph, and we have to apply the Euler criterion, the Euler circuit criterion. So we have to calculate the degrees of this graph. This one is 1, 2, 3, 4, 5. That's what we mentioned, right? So 5. This one has 1, 2, 3, 4, 5. Yes. This has 1, 2, 3, 4. Oh, that's good. An even one. 1, 2, 3, 4, 5. That's not good. 1, 2, 3, 4, an even one, and 1, 2, 3, 4, 5, 6, 7, 8, 9. That's too many, right? There are 4 odd degrees, and there should only be 2 for me to have there an Euler path even. Forget about circuit, but path. And double checking that I've calculated everywhere well. For F has 1, 2, 3, 4, 5, 6, 7, 8, 9 doors. Okay, A has 5, B has 5, and D also has 1, 2, 3, 4, 5. So the degrees here is the number of doors that you have being in that region. How many doors are there available to you? Okay, for F, remember it's the whole outside part. So each of these doors belong to give you access to the house, if you want. So again, but for a less obvious reason, this is no path, no Euler path. And therefore it's impossible. So if you try to do this, you'll see what happens is you keep going and you can go, but now you're stuck here. You're inside B. There is no way to go outside B anymore because all the doors have been used, right? Remember, this door has been used already, okay? So there. Okay, but it's a different application of our circuit, but I want you to know these things. And then finally, one more drawing like this. I'll do it here. It's a rectangle, and then we have this zigzaggy thingy in it. And this zigzag thingy. Okay, so this picture, can this be drawn without lifting your pencil and without going back? Retracing. Okay, same we look at all the intersections that become the vertices of our graph, and then the line segments are become the edges. Okay, so we calculate the degrees. 2, 1, 2, 3, 4, 1, 2, 3, oh, not 1, I don't like odd ones, 1, 2, 3, 4, 2, 1, 2, 3, 4, 2, I like that, 1, 2, 3, 4, 5, and 1, 2, 3, 4. Aha, that's good news. There is exactly there is exactly 2 odd degrees, so 2 odd degrees. That tells me there is going to be an Euler path, not a circuit. That is not a circuit. But that's fine enough, because it is about drawing this whole thing without lifting your pen. And this is an Euler path, because an Euler path is exactly going to each line, every edge once, which means drawing each line segment once, and that's enough. But it tells me more. It tells me I will have to start at one of the odd degree ones. So now we have to design that path, and so we need names. So I call this A, B, C, D, E, that's a weird E, F, G, H, and I. But that's one thing to do. Since we have an Euler path, but we have really no criterion for Euler circuits, I'm going to add, let me do this in green, I'm going to add one more edge connecting the odd ones. Let me not write that down. So this is the edge that I'm doing. Now this is a green edge, and I'm going to keep track of that when I use that, because I now have a new graph, and we're going to just look for an Euler circuit in this green graph. But at the end, I have to deal with that green one. I can never use that green one. So what it be is I'm going to run around, and at some point I work off the green one, and I'm finished. And I start and end in G, say. Now, I will have at some point worked on green, and I'm not supposed to do that. So I go trace my steps back, and I say, okay, when was the time that I used green? Let's, instead of starting from G, let's start from the point where I don't know which way it was, either here or there, one of these 2 points I will be. I trace back my steps, right? I say, I'm tracing back my steps, it leads me here. And then I would have to do the green one. I say, no, I'm not going to do that. I'm going to now start from here and do the same path, but starting from there, because then the very last one I will do is this one. Okay? You'll see it in action. So pick anything. And I don't have to pick D, I can pick whatever I want. I'm going to pick A. So pick a vertex. And that is going to be A, and a vertex plus a circuit, using that vertex. Okay? So I'm going to make it simple. I'm just going to walk around the block. I don't want to think too much. I'm just going to say A, B, C, F, I, H, G, D. Hey, you see, it's already quite a good path, right? Now, what happens? 2 things. There are certain vertices that I have visited. That's important to know. And now there are certain edges I can no longer use. And that's the next thing I have to keep track of. I have to delete those. Now, I can use my delete function, but I'm going to trace them, I'm going to make them red. Or you could kind of scrap them out, do something. Now, of course, if you present this answer to me, if you start scrabbling and making a lot of notations on one single graph, then I don't know anymore what you did. So you're going to have to present it a little bit in steps. Okay, so this is the graph. After this graph, I don't know how to do this. I'm the advantage of using a dynamic iPad where I explain things, right? But okay, here we go. So this one, this means I have visited A, I have visited B, I have visited C, I have visited this guy and use this edge, I visit this guy and use this edge, this guy, this guy, this guy. Okay, so anything that is red cannot be used anymore. I mean, any edge that is red. Of course, the vertices that can be still used. But notice, for instance, this means this vertex is done, and so is this vertex. But there are vertices left. Now, the next thing, I do the same thing. So I keep doing the same thing. Pick a vertex, but there is one condition. Pick a vertex that is on a previous path. I'm going to, or circuit. Well, let me go say circuit. Well, path circuit, it's the same thing. Why? Well, that's because I have to glue them all together, and in order to do that, I have to make sure that I can do that. Okay, and so I have to pick one of the vertices on that red path, but not, of course, any edges. I cannot pick A because A has nothing to show anymore, so I'm going to pick D. So I pick D, and I'm going to, okay, let's go pick D, and I'm saying I'm going to do this. I'm going to go around like that, and then, okay, I'm going to take the green. Let's see what happens if I take the green. No, sorry, I want to make it a little bit, sorry. Let me not do that, sorry. It's actually a good choice, but I want to do a bad choice so that you see you still can work it out. So I'm going to do, well, bad. There's nothing bad, but I'm going to pick B. Why not? Because alphabetically that seems to be the next one to do. And then the path I'm going to take is, I'm just going to go this. Let's go this way. No, what do I want to do? Okay, I'm going to, yes, I want to take the green. I'm going to take the green one at this point. As I said, let me show you how do you do. So B, C, but then from C to D, that's a green one. And then from D to B, what does that mean? It means it's a one that is, and to emphasize that, you can either make one of the vertices green or both of them, as long as you know what it means. This is to remind me that this edge is actually not an edge in my graph, and in the end we will have to deal with that. At the moment I'm not going to deal with that, so that's it. That means, oh sorry, no, people, you should have protested. I used the edge BC, that's not a valid edge anymore. No, sorry. The path I'm going to take, I wrote down the wrong path, right? I was going to from B to E, and then to C, and then to D, and then to B. So the path this is the path, because I was walking on an edge that was red already. That's not allowed. But the whole point is that D and C are, C, or now it's from C to D, that's the green edge. So let me mark these two colors that I remind myself this is a special edge that is not part of the original one. Okay, so what does this mean? Okay, what have I used now? This one, this one, this one, and this one. So I need to pick a vertex again, but it has to be a previous vertex. What can I pick here? In fact, now it doesn't matter. Whichever is available, I'm going to pick E. Oh, if you want to pick the alphabetically first, or the alphabetically first one is D, I guess. So pick vertex. Well, let me not remind. Let me just copy. I'm going to pick one here. So there's one there. I'm going to pick D. So and then what can I do? Well, actually, you have no more choices here. Well, except for the orientation, the direction that I walk in. Let's walk clockwise. So from D I can go to E, then I have no choice, I have to go to F, from F I have to go to H, and from H I return to D. Okay, that's one solution. The other solution, of course, the counterclockwise. But that's the only two that I have now. So, let's mark this, nothing left, I'm done. The only thing I need to do is, now the last step is put it together. And how do you do this? Well, we know that this B was in the previous part and was there. So we start with our first part. But then we reach one of these vertices and we say, wait a sec, when I'm in B, I'm going to do my little detour. Okay, so let's do that. So I'm going to combine these two parts first. So this is A, and now I'm in B and say, okay guys, I'm going to take a little detour, because I figured out later that there's a detour that I can use. E, C, C is a green one, so let me keep them green. I keep them green here because I need to remind myself of this special edge that I used. I'm back in B, and now I can continue with whatever I is left. You see that? Okay, so that takes care of these. So these two are now made into a single part. Now I have to combine these two. I know that this D must be in the previous graph. In fact, it's there twice, and I have the choice. I can insert this D here, or I can insert the D there. Doesn't matter, I'll do it in the first position, I guess. It's the most obvious one, B, E. This is green one. I have to remind myself that this is a special edge here, from C to D. As you said, you could, yeah, okay. as long as you mark it somehow. Now I am in D, and now I tell myself, okay, guys, wait, I have a new detour that I just found. There's this detour, I'm going to take that. So that is D, E, F, H, D. You're back in D, that's now no longer green, right? The green edge is over there. And then finally, continue where I was. Where was I? I was here, right? So now continue with this part. That is B, C, F, I, H, G, D, and A. There is my circuit. However, this circuit is not what I want, because when I would draw it, I would be A, B, let's see, A, I'm going to make it a bit smaller. So it would be A, let's trace it down with a different color and do it in brown. No, that's too much similar. Let's do it in white. No, that's perhaps not work. Can I not choose a blue? Let's do. Okay, so A, and let's take a bit bigger perhaps. A, and then from A to B, and from B to E. That's not E. Where is E? From B to E, from E to C, from E to D. But this is not from C to D. This is not part of the original graph. So I'm stuck, and that's what I said. When I'm stuck, I'm saying, okay, instead of starting from A, let's start from this part here, D, just after my uses of the edge, so that this edge now becomes the last edge in the whole circuit, and therefore I don't take it. That's perhaps the easiest way to say. So in other words, you now look at the end of your bad edge, the end point of that new edge, and you start from there. So D, E, F, H, D, B, C, F, I, H, G, D, A. So this is A here. Now this A is the same A, so don't write a double. B, E, C, that's here. But now I don't write D anymore, because I cannot use that. This is the only one I cannot use. But now I start from D and end in C. So I would start from D and end in C if you want to. Oh, I cannot do this. So again, I'm going to do this in a different color. Let's do green, I guess. I'll make it even bigger. So it is start from D, then you go to E, F. Yeah, I'm going to lift, otherwise the thing starts making weird. H, D, B, C, F, I, H, G, D, A, B, E, A, B, E, C. That's where I stop. Okay, I started from here and I ended there, which is what happens to happen. I have to start in an odd degree, end in an other odd degree. And if you would do if you want to start it from C, well, okay, then just go the other way around. Okay, so that's how this problem on Euler circuits will be. I will ask you something like that. So either a problem of drawing, or a problem where you have to kind of a Königsberg, where you have like a situation with a homework problem like that too, where you have to make a graph out of the situation, and then offer this as a multigraph, and then check whether it is possible or not. All right.